All right. Day 2 of 2.3. Still dividing polynomials. We're just going to use a different method. One that you're going to like. It's called synthetic division. It's got some drawbacks, though. It's a faster, better way to divide polynomials, but it can't always be used. Okay, it's not like it's too good to be true, where it's just going to totally eliminate having to do long division. That'll still come up because there's cases that's the only way to simplify. So here's the first question to address. When can you use it? When you are dividing you might think back to the first day and you're like, hey, those are cases that we had. When you're dividing by x minus k, right? Now if you want to refer back to that first day, example 1, 2, and 3, I believe we had the right form. Okay, if I'm remembering those examples correctly, we could have done synthetic division. Example 4, we were dividing by a quadratic. That doesn't fit this at all. Okay, when can't we? Unfortunately, the answer here any other time. Any other time. Okay? So it's not like it's going to, allow us a shortcut all the time. All right, so let's do one. Setup is long division. But I notice right away here with my divisor, that is x minus k. Now here you got to be a little bit careful. It's always x minus k. Now if I were to put it in the exact form that we're talking about, k, which will come up more and more in the next examples, is -3. Okay? So now to do synthetic division, that's the number I need to start with. And it looks kind of interesting. I set it up like this with a 1, 0, -10, -2, and 4. Okay? Just the coefficients. Okay? Just the coefficients. I then bring down the 1. The number that I bring down, I always multiply by my value of k, which would be -3 times 1, which would be -3. 0. Now this is the one place where you could kind of trip up on synthetic division a little bit. When we were doing long division and we were kind of working our way down, we always subtracted terms. With synthetic division, you add them. Okay, that's just something you're going to have to be careful about and do whatever you need to do to make sure that you can keep that straight. Okay, so 0 plus -3 is -3. I'm getting a 9 there because I multiplied -3 by -3. I get 1. Excuse me, -1. Which would give me a +3, which would be, that would add up to 1. Okay. Now some will make the mistake of stopping here, and you shouldn't, okay? Because I should still have a polynomial as my answer, just like I did with long division, because look back at our original problem. We were taking that big, long, 4th degree polynomial, and we were dividing it by x plus 3. Okay? I should get something that looks like that for a final answer. Okay. Just for as far as the name, you've probably noticed that when I'm talking about my quotient, right? Because you get a polynomial as your answer. I just keep calling it q of x. That's the quotient. It's not the first two that I divided, but this one, this new one, as an answer. Those numbers that we got are all the coefficients. X to the third. How did I know to start at x to the third? Because of the one and only case you can use synthetic division, it always reduces the power that you started with. It always reduces that by 1. Okay, so I notice right here I started with an x to the fourth. My quotient is going to be x to the third. And then we just work our way down. Minus 3x squared minus x plus 1. And what's going on at the end? Oh yeah, that's our remainder. Okay, and that's actually in the next two examples. That's a number we want to talk about more because it's pretty significant. And just like before, that remainder goes over our divisor, which in this case was x plus 3. Okay? And there you have it. All right, that is synthetic division. It's nice. It's faster. When you are able to use it, you should use it. Okay, it's a better alternative to long division. Now, as I said, let's talk more about that remainder. Okay? Because synthetic division, another nice thing about it is we can use it for more than just dividing, two polynomials to get this new one, right? The one that I called q of x. We can use it for a little more. All right, that remainder is a pretty significant number. Okay. Here's what this is saying. Okay, this remainder theorem. That if you take a polynomial f and you divide it by x minus k, okay, that's the situation we're talking about, right, where you can do synthetic division. The remainder is what you would get if you plugged in k, all right? So now, in a minute here, I'm going to do synthetic division with -2, okay? When I do that, keep in mind that is like, for this problem, that is like dividing by x plus 2. Okay? Now, first of all, let's just evaluate. All right, now this is one of the nice things about it, because this would be a little bit tedious to do. Even if you plugged it into a calculator. I got this cubic polynomial here. And if I wanted to plug in -2, worst case I could do this by hand, which you could, okay? Not that I would make you, not that you would want to, but you could do it. You would just simplify term by term. It's really just doing a bunch of addition and multiplication. I picked a nice long polynomial to show that evaluating them can be a bit tedious to do. It's kind of the downside of polynomials. The situations they represent and the information that you can get from them, especially in application problems, can be very valuable. They're just tedious to work with because they have so many terms. Okay? The deal here is this would come out to be -9, right? That had nothing to do with synthetic division. That's a function, right? We plugged in an x value of -2. We get this y value of -9. Okay? Now the best case, way to go about that would be to plug the whole function into our graphing calculator to make a table. Okay? That still wouldn't be great because the table is really useful if you want lots of solution points accurately and quickly. Okay? Well, we just wanted one, right? This was the whole question here was, what do we get when we plug in -2? This might be the fastest and the best option that you have. All right? Let's go to synthetic division. Again, I want you to think of this from the perspective of we just want one single point. I want to evaluate at -2. Now, if you look at the name of this theorem and what I just did, I'm laying on the hints pretty thick. You should have a really, really good expectation of what the remainder is going to come out to be. I hope at this point that you're thinking, bet you it's going to be -9. Well, let's just verify that that's the case. That's exactly what I'm expecting. -2 times 3 is -6. There's 2. -2 times 2 is -4. There we would get +1. 1 times -2 is -2. And oh my goodness gracious. There it is. Okay? So that's more than just the, the remainder. Synthetic division, again, if you needed to evaluate a particular point, just one point, and you wanted to do it quickly, this would be the way to go. You might be thinking, well, I just do what we did before, what we have in blue, where I just punch all that into the calculator. If you get good with synthetic division, because it's a pretty simple set of steps to follow, I bet you the work I have in red, doing that by hand versus typing the line in blue into your calculator, I bet you could do the synthetic division faster. Okay, and it's not that prone. You mean you could make a mistake doing it, but the steps aren't super terrible. Okay, so that's something to keep in mind about it as well. Now, this leads to another little consequence, something that's a big deal for us, right? I got a nice, big 5th degree polynomial, okay? Because the factor theorem is really based on the remainder theorem again, okay? But now it looks at what's going on if we got a remainder of 0, okay? Well, let's do that. Let's look at that exact case right here. Now, keep in mind with these two, the numbers that I want to look at here for this factor are x equals 2, and -3. Okay? Same set of steps before, a little bit longer here, which is fine. -4, -27, and -18. Okay? Now, as we go through the synthetic division, I bet you have an expectation, based on the factor theorem here, of what's going to happen. Okay? As far as our remainder goes. 2 times 2 is 4. 7 plus 4 is 11. 2 times 11 is 22. -4 plus 22 is 18. 36. 9. 18. And our first case where we see 0. Okay? Now, what is the factor theorem telling us here? Okay? First of all, f of 2. Like if you were to plug that into the polynomial, this goes back to the remainder theorem, right? If you plugged in 2, you would get 0. All right? Now, if you think back to section 2 where we did some graphing, this is a big deal for us. X equals 2 is a 0. Okay, when we were graphing polynomials, which we're going to do a lot more of, we needed to find zeros. That was like the number one thing to get like a feel for the graph was, where are the zeros, and then what are the tails doing? And then we could just plot some extra points from there to kind of figure out what's happening. Okay? And we had said as far as zeros go, we need to factor. Well, we got a fourth degree polynomial that I have no interest in factoring. Okay? There's a way to do it. We're not interested. Okay? It's not going to be pretty. Let's pass on that. All right? But here's the other thing. If x equals 2 is a 0, x minus 2 that's a factor. What I'm really concerned about here is that with the remainder theorem and the factor theorem, that when you do synthetic division, that you're clear about all the information that you get, particularly if you have a case where the remainder is 0. There's a lot it tells you. Okay? Let's do another round. I don't need to go out to that 0. Now I'm going to do negative 3, and it says, show that x plus 2 is a factor. So k is negative 3. I bring down the 2. There's negative 6. We get 5. That would lead to negative 15. 3. Negative 9. And of course, 0. Okay? So again, if you plugged in negative 3 for an x value, you're going to get 0 for y. X equals negative 3 is a 0. Okay? And x plus 3 is a factor. Sorry about that. I think I bumped back to the previous slide on accident. What was I saying here? Now the last thing I want to show you here is, alright, if I go back and write out f of x, this is kind of a nice thing that I can use it to find some zeros but don't need it to find all of them. This could have as many as 4 zeros. Okay? I've already shown that I could take out a factor of x minus 2. And I've shown that I've got a factor of x plus 3. What's left? Remember, each time I do synthetic division, it reduces the power by 1. So now I look to here, and after I've taken out those two factors, I still have a quadratic left. So remember, I didn't want to factor that fourth degree polynomial when we were getting started because that just sounds terrible. Okay, factoring a quadratic, I think we can do that. That doesn't seem so bad. But here's the other big thing. If you find a couple zeros with synthetic division, okay, and you get it reduced to a quadratic, it actually isn't necessarily about factoring anymore, though we'd like to check to see if we can. Okay, for example, right? Every time I have a factor, I can set it equal to 0 and solve, right, to get my zeros. Whoops. That should be, we had x plus. This one actually is, you can split it up 2x and x, and there's really hardly any factors to check here at all. Just 3 and 1, that's where they go. Okay, I could take those last two, set them equal to 0, and solve and get my last two zeros. The other thing, though, is if it hadn't been factorable, I could have just gone to the quadratic formula. Okay, and now remember, we're not going, much above 4th or 5th degree. So if we can somehow find these first 2 or 3 zeros with synthetic division and get what's left over after we take out some factors down to a quadratic, you've automatically got the last two. Again, the quadratic formula isn't necessarily a ton of fun to use, but you get the numbers plugged in and simplify, and it guarantees you're going to get the last two zeros. Okay? Which is nice. We don't have to worry about, do we have any method to find them or not? We know that we do. Okay? So you can quickly divide polynomials. You can quickly evaluate them. Okay, that's what we saw in the second example. And then in particular, if you get a remainder of 0, you've got a point like an x value that's a 0, and you're talking about a factor of the polynomial. Okay?